After the first 3 chapters, we have now finished the introductory part of this course. It contained an overview of the material and what to expect from this course, and a review of basic concepts from linear algebra that everyone should know before starting with the rest of the material. And moreover, the purpose was to provide a little motivation for studying the rest of the material in this course. With this chapter, chapter 4, we really start to dive into the core material. In particular, we start to define vector spaces in an abstract algebraic form, and the chapter is therefore called the algebra of vector spaces. So, what does it mean when we speak about abstract vector spaces? So far, we have come to think of vector spaces as spaces of little arrows that point in a particular direction. This already gets a little bit difficult when we think of vector spaces in dimensions higher than 2 or 3. It gets even more difficult if we think about complex vector spaces. But in fact, even all of these vector spaces, so the ones with dimensions higher than 3 and complex vector spaces, only make up a small fraction of the set of all possible vector spaces. I've tried to illustrate this fact by a little diagram up here, where the rectangular box is supposed to represent the set of all vector spaces. And we see that the sets that we typically associate with vector spaces, such as Cn or Rn, or even R3 or R2, is just a tiny fraction of the set of all vector spaces. So there are many more vector spaces out there that we typically do not associate with vector spaces because they look different in nature. If that is true, you may ask, what exactly is a vector space? And the answer to this question is that a vector space is defined by an abstract algebraic definition, which has these known vector spaces here as special cases, but which allows also the definition of many more possible vector spaces. So in this chapter, we'll get to know about the basic algebraic structure that's really at the core of every vector space. And in the next chapter, we will get to know some geometric structures, which are often found in some common vector spaces, such as the particular vector spaces that we know very well. However, the commonly known vector spaces still remain particular examples of such vector spaces even with the geometric structure. Let's begin with the definition of a field. A set F that we write with this blackboard bold letter is called a field if there are 2 binary relations defined on F, which are called an addition, that's denoted with a plus sign, and a multiplication, that's denoted with a dot. And these 2 relations on F must satisfy the following properties. For all elements alpha, beta, and gamma in F, we must have, first of all, closure, in a sense that if we apply the addition to any 2 elements of F, we will get another element of F. If we apply the multiplication to 2 elements of F, we also remain in F. Then second, we must have commutativity. So if I add alpha to the addition of beta and gamma, this must give the same element of F as if I first add alpha and beta and then I add gamma. And the same thing must hold for multiplication. The third property I must have is distribution. So if I multiply the sum of 2 elements, alpha and gamma, with a third element alpha, this must be the same as multiplying alpha with beta and adding to this the multiplication of alpha and gamma. Fourth, there must exist identities. First, there must exist an additive identity, which we denote with this 0 inside the field. And additive identity means that if I add this identity to any element alpha, I get my original element alpha back. Similarly, there must exist a multiplicative identity that we denote with a 1, and it must be an element of the field. And the property of the multiplicative identity is that if I multiply alpha with the multiplicative identity, I get my element alpha back. And the fifth and final property that we need is the existence of inverses. So first of all, for all elements alpha of the field, there must exist an additive inverse, meaning an element that we call minus alpha in F, and which has the property that if I add this element to alpha, then I get my additive identity. And a similar thing must hold for multiplication. So for all alpha in the field, except for the additive identity, there must exist a multiplicative inverse that we call alpha to the minus 1, and which must be an element of the field. And it has the property that if I multiply alpha with its multiplicative inverse, I get the multiplicative identity. We will also refer to the elements of a field as scalars. When reading through definition 4.1, you may have realized that you already know some particular fields. In particular, the set of all real numbers R, the set of all complex numbers C, and the set of all rational numbers Q are particular examples of fields. However, and that's important to notice here, these are not the only possible examples of fields. In fact, any set that satisfies the conditions stated in definition 4.1 is a field. And there are many more examples of fields which are not these three very well-known sets. That being said, the two main fields that we will be working with in this course are the set of real numbers and the set of complex numbers. However, not everything we know in mathematics is a field, of course. So for example, our 2x2, the set of all real 2x2 matrices, is not a field under the usual matrix addition and matrix multiplication. And also Rs, which denotes the set of polynomials in S with real coefficients, is also not a field under the usual polynomial addition and polynomial multiplication. It's a good exercise to pause this video now and take a moment to think about why these two are not fields. To see this, of course, you have to go through all the points in definition 4.1 and check whether they are satisfied for these two examples. And if we do this for the set of all real 2x2 matrices, we will realize that there are matrices, such as this one, that has no multiplicative inverse, because it's not invertible. If we do this for the set of all real polynomials, we realize that the polynomial S has also no multiplicative inverse. The inverse would be 1 over S, but this is not a polynomial. Definition 4.2 is now the abstract definition of a vector space, and it says that a vector space that we denote like this is a set of vectors that we denote with a bold letter together with a field F and two operations that we call vector addition, and we write it with a plus sign. So we use here the same sign as for the field. and a scalar multiplication, for which we use a little circle, such that the following properties must be satisfied. For any two elements alpha and beta in the field and any vectors x1, x2 and x3 in the vector space, we must have that the following 6 properties are satisfied. First, the vector space must be closed under addition and scalar multiplication, meaning that if we add any two vectors in a vector space, we will end up again with an element of the vector space. And same thing for the scalar multiplication. If I multiply any vector with any scalar in the field, we want to end up again with an element of the vector space. Second, we want commutativity, meaning that for any two vectors, x1 and x2, x1 plus x2 is the same vector as x2 plus x1. Third, associativity. So I can add x1 to the sum of x2 and x3 and get the same vector as if I first add x1 and x2 and then add x3. And similarly for any two scalars alpha and beta, if I first multiply a vector x1 with beta and then with alpha, I get the same vector as if I first multiply the two scalars together and then multiply this with the vector x1. Fourth, distribution. If I add two vectors x1 and x2 and multiply the result with a scalar alpha, then this will give me the same vector as if I multiply the scalar alpha with x1 and the scalar alpha with x2 and then add the two resulting vectors together. And also we want a second type of distribution. If we first add the two scalars together and then multiply this with the vector x1, we get the same result as if we multiply each scalar with the vector x1 and then add the two vectors together. Fifth, identity. There must exist a zero vector in the vector space, and we write the zero vector with the 0 with an arrow on top, such that for any vector x1, if I add this zero vector, I will get my vector x1 back. And moreover, there has to be a multiplicative identity that we denote with a 1 in the field, such that if I scalar multiply a vector x1 with this multiplicative identity, I get my x1 back. And finally, the sixth property is that we must have an additive inverse. So for any vector x1 in the vector space, there must exist a corresponding additive inverse that we denote by minus x1 in the vector space, such that if I add to my vector x1 the additive inverse minus x1, I will get to the zero vector. When going through this definition, you may have mentally checked for yourself that all of the known vector spaces, such as R2, R3, Rn, and so on, easily satisfy all of these conditions. So then, what's the point of having this definition? Well, the point is that, of course, R2, R3, Rn, and so on satisfy these conditions, but they're not the only ones that satisfy this definition. In fact, there are many more vector spaces that satisfy this definition, and so R2, R3, and Rn are just special examples of abstract vector spaces. Before we continue, this slide contains a few remarks on notation. First, fields are denoted with blackboard bold letters, such as this F. Vector spaces are denoted with uppercase bold letters. As already mentioned, we will work exclusively with the fields R and C. There are in fact more fields that are of mathematical interest, but they have no practical relevance. And therefore, whenever we write F for a field, we mean either R or C. where appropriate, we will be brief and abbreviate the vector space, which is always a combination of a set of vectors and a field, simply with the vector space V, because in these situations the field that we use will be obvious. We will also often suppress the cumbersome notations of the multiplication dot of the field and the scalar multiplication of the vector space. There will be also no notational distinction between the zero of a field, so this zero, and the zero vector of the vector space. So we will basically omit this arrow for the zero vector and just use a zero for both. Now let's look at some examples of vector spaces. As already mentioned, of course, the classical vector spaces, so Rn with the field of the reals and also Cn with the field of the complex numbers, are vector spaces for any number n in the natural numbers. Moreover, the set of polynomials Rs with real coefficients together with the field of the reals is also a vector space, which you can easily check by going through definition 4.2 and realize that it satisfies all of the requirements. But it turns out there are many more sets that satisfy the conditions posed by definition 4.2, and that's what we're going to look at next. Another important class of vector spaces are sequence spaces. So spaces where the set of vectors V consists of infinite sequences. This means that a vector that we denote with x, so an element of the vector space, is actually an infinite sequence of numbers. And these numbers are elements of the field, so they can be either real or complex numbers. Sequence spaces actually make up a whole family of vector spaces. And here are three important examples. The first one is the sequence space L1, which is the set of all sequences that satisfy that the sum, the infinite sum over all of its elements of the absolute values of the elements of the sequence is bounded, so it's less than infinity. And this is called the set of summable sequences. The second important sequence space is the space L2, which consists of all infinite sequences that satisfy that they are square summable. So now we take all of the elements of the sequence, which is an infinite sum again, but now we take them squared, and this has to be bounded, so less than infinity. And finally, the sequence space L infinity, which is the set of all sequences that satisfy that all of its elements, xk, in absolute value are bounded by some finite number. So these are infinitely many elements, obviously, and they always all have to be less than a constant c for all k in n. And this set we call the set of bounded sequences. It's a simple exercise to verify that these three sets, L1, L2, and L infinity, are vector spaces because they satisfy all the conditions of definition 4.2. And in fact, there are many more sequence spaces which are also vector spaces. Another important class of vector spaces, according to definition 4.2, is made up of so-called function spaces. For function spaces, the set of vectors V consists of functions. So for instance, functions that map from a finite interval, AB, into the real numbers combined with the possible values minus infinity and plus infinity. Now you may think that functions and vectors are two different things, but for certain classes of functions that we're going to look at next, you will see that they actually satisfy all of the conditions of definition 4.2, and hence they represent an abstract vector space. Such a vector space where the vectors are actually functions are called function spaces. And clearly in these function spaces, the vector addition is defined as the pointwise addition of two functions, and the scalar multiplication is defined as multiplying a function with a scalar value. And here are some important examples of function spaces. First, the set CAB, which is defined as the set of all functions which are continuous. So it's the set of all continuous functions. Particularly relevant are also the so-called Lübeck spaces, of which we have the three most important examples here, L1, L2, and L infinity. And L1 is defined as the set of all functions which are absolutely integrable. So if I take the absolute value of the function f of x and integrate it over its domain from a to b, then this value has to be bounded, so less than infinity. For L2, we take the set of all functions and take the absolute value of the function squared and integrate it over the domain, and this value must be bounded. And finally, the Lübeck space L infinity, which consists of the set of all functions such that the function is bounded in its absolute value for all values x in the domain of f. So there must exist a c that's not infinity, so it's less than infinity, such that f of x is less than c for all x in the interval ab. And this is called the set of all bounded functions. One important thing to remember about sequence spaces and function spaces is how large they are. So which of the spaces contains which other space as a subspace. In fact, for sequences, we have that little L infinity is the largest space, and it contains little L2 as a subset, where again little L1 is a subset of L2. For functions, it's the other way around. So large L1 is the largest space, and it contains large L2, and large L infinity is the smallest of the function spaces. These containments are stated again as a remark on this slide. It's a good idea to think a little bit about these containments and try to verify them for yourselves. Because we were talking about continuous functions on the previous slide, for the sake of completeness, definition 4.3 states the classic definition of the continuity of a function. This definition is based on a classical epsilon delta argument that you encounter everywhere throughout the field of mathematics. And we will also come across this epsilon delta argument a couple of times throughout this course. But for now, let's just recall what it formally means for a function to be continuous. So first, a function that maps from an interval AB into R is said to be continuous at a certain point in this interval if, for all epsilon greater than 0, there exists a corresponding delta in R, such that if x in the domain is close to x bar, and close means delta close, then also the function value f of x will be close to the function value of f of x bar, and close here means less than epsilon. What's important here is that for any epsilon, I must be able to choose a delta, which may depend on epsilon, such that these conditions here are satisfied. So this is what it means for a function to be continuous at a certain point in the domain. Now, if we say that f is a continuous function, then what this means is that f is continuous at every point x bar of its domain. Now we have defined what's a field and what's a vector space over a field, and we have seen several examples of vector spaces and new classes of vector spaces, such as sequence spaces and function spaces. Next, we define a very fundamental concept for vector spaces, and that's a linear combination and linear independence. So let V be a vector space over the field F, and let xk be a finite set of vectors in this vector space. By the way, we use this notation here to mean the set of vectors x1, x2, and so on up to xn. An expression that sums up these vectors, where each vector gets multiplied by a corresponding scalar, is called a finite linear combination of the vectors in this set. This idea can be generalized to infinite linear combinations, where we take an infinite set of vectors and multiply each of these vectors with a corresponding scalar, and now make an infinite sum over all of these scalar-weighted vectors, and call this an infinite linear combination of the vectors in this infinite set. Here, for example, the infinite index set that we have denoted with a k could stand for the set of natural numbers, and then this set here would be the same as having a sequence of vectors x1, x2, x3, and so on. Based on this, definition 4.1 defines the very important concept of linear dependence. So let V be a vector space over the field F, and consider a finite or infinite set of vectors xk in the vector space V. So in this case now, the index set k can be a finite or infinite set. And then this finite or infinite set of vectors is called linearly dependent if there exists a non-trivial linear combination, so finite or infinite linear combination of these vectors that equals to 0. Here the expression non-trivial is critically important, and what it means is that not all of the scalars alpha k that multiply the vectors xk in the linear combination may be 0. Conversely, we can say that a set of vectors, finite or infinite, is linearly independent if the following condition is met. If we put any linear combination of these vectors to be equal to the 0 vector, then this must automatically entail that all of the scalars alpha k must be equal to 0. And if that's the case, then this set is called linearly independent. We probably all have a very good intuition of what linear independence means on a classical vector space such as R2, R3, or even Rn. But in order to get a little more familiar with other types of vector spaces, in particular function spaces, let's also look in proposition at what linear independence means on a function space. In this case, on the space of continuous functions on the interval -1 to 1. And in this case, we take the functions fk of t to be the corresponding powers of t. So f1 of t would be the function t, f2 of t would be the function t squared, f3 of t, t cubed, and so forth. And in proposition 4.6, we want to show that this infinite set of vectors is linearly independent. For the proof of proposition 4.6, consider the infinite linear combination of functions fk and set this infinite linear combination to 0. If we want to show that the functions fk are linearly independent, we have to show that this implies that all of the scalars alpha k must be equal to 0. First, let's substitute the definition of the functions fk of t into the infinite linear combination. And what we get from this is that this is equal to alpha 1 times t plus alpha 2 times t squared plus alpha 3 times t cubed and so on. And this is equal to g of t, where g of t is the 0 function. So by writing it like this, we've just made it more explicit that this 0 here actually stands for the 0 vector, which is in this case the 0 function. Now, even though the single functions fk of t are just continuous and we don't know anything about their differentiability, by the assumption that the infinite linear combination is 0, we know that the infinite sum here, or this expression, must be infinitely differentiable because it's equal to the 0 function, and the 0 function is infinitely differentiable at the point t equals 0. And in fact, all of its derivatives are 0. Therefore, we can take derivatives of both sides of this equation of increasing order, and what we get is the following. The first derivative of this infinite sum is equal to alpha 1 plus 2 alpha 2t plus 3 alpha 3t squared and so on. And the first derivative of the right-hand side is equal to 0 because g of t is the 0 function. Now, if we substitute t equal to 0 here, then all of these terms of higher order also will drop out. And what we're left with is that alpha 1 needs to be equal to 0. Next, taking the second derivative of this infinite sum yields 2 alpha 2 plus 6 alpha 3t and so on. And again, this must be equal to the second derivative of the 0 function, which is 0. And we can now substitute again t equal to 0. So all of these terms from alpha 3 upwards, they drop out. And we're left with the condition that alpha 2 must be equal to 0. Taking the third derivative yields 6 alpha 3 plus 24 alpha 4t and so on, which again must be equal to 0. And again, all of these terms that contain at least a t, they all drop out for t equal to 0. And we get that alpha 3 must be equal to 0. Clearly, this process can be continued indefinitely. And what we will get is that all of these alphas need to be equal to 0. To summarize, we have shown that the only way this infinite linear combination of functions equals to the 0 function is by having all of these scalars alpha k being equal to 0. And hence, we have shown that the set of functions fk is linearly independent.